Here is another exercise, exercise 8 of chapter 13, where I'm going to show you a way to create random data that you can use for evaluating data analysis methods and continuing to learn more about linear algebra. In this case, let me scroll down here. The goal is to create a data set of n by t. So I have often think about this in terms of time series, multivariate time series analysis. So n channels by t time points, but more generally, this is n features by t observations. And we want this multivariate data set to have a particular correlation matrix. And that correlation matrix should look like this. So the question is, how do you create a bunch of random numbers such that those random numbers organized into a 3 by 10,000 data matrix have this correlation matrix? And the answer is this. This is the formula. So you start with just totally random, uncorrelated numbers. We call that matrix X. And then you create your correlation matrix R, and then you implement this formula here, where Y is going to be your uh, random numbers matrix with this correlation structure. So lambda here and V are coming from the eigendecomposition of this correlation matrix. So you create this correlation matrix, extract its eigenvalues and eigenvectors, take lambda to the 1/2 power, pre-multiply that by the eigenvectors, and that is like a multivariable filter, which you then push the uncorrelated data through, and then the output of that is the correlated data. So implement all of this in Python, and then compute the empirical correlation matrix of X, and actually it should be Y. So the correlation of X should be basically the identity matrix, although there's going to be some, because we're sampling a finite number of numbers here, it's going to be some little numbers other than 0 here, but it should be somewhat close to the identity matrix. And then compute the empirical correlation matrix of data Y. Sorry for this typo here, I'll fix that. Again, that's not going to be exactly identical to this matrix because of random sampling variability, but it should be pretty close. So here in the code, we have the matrix R. These are the correlation coefficients that we want in the data. And then we have the eigendecomposition of that correlation matrix. We need to convert the eigenvalues into a capital lambda matrix, which is basically just making a diagonal matrix with the eigenvalues on the diagonal. And then here is just the direct implementation of the formula. And now I see why I got confused in the book, because in the book I call this matrix X, and then I call this matrix Y, and I computed X on a separate line of code. Okay, so my apologies, although it's likely that by the time you are watching this video, depending on when you purchase the book, you might not even see that typo in the book. So anyway, and then here is the observed correlation matrix, which should be pretty close to R. So let's see what we have here. So this is, in fact, I think maybe what I'll do is say X, correlation of X minus R. And yeah, now you can see, well, the diagonals are always ones, so that error is going to be very small. And you can see the off-diagonal elements, the errors are small. This is 10 to the minus 2, 10 to the minus 4, and so on. So yeah, it's not exactly what we requested up here, but it should be quite close, given random number selection.